Here is a combined summary of the two pages. The standard model, SM, does not have flavor-changing neutral current, FCNC, processes at the tree level, making them tightly constrained by data. Typically, the lower bounds on the scale of new physics obtained from KK and BB mixing lie well above 10 TeV, beyond the reach of current and future colliders. This paper demonstrates, using a specific Z model featuring flavor-changing interactions, that such limits can be severely weakened by specific choices of the quark mixing matrices with no prejudice while maintaining the CKM matrix in agreement with the data. Flavor physics has been crucial in developing the SM, and most SM parameters are related to flavor physics. Flavor physics processes can constrain very high energy scales well beyond accelerators. However, the authors argue that the LHC and high luminosity LHC, HL-LHC, are promising probes for flavor-changing interactions mediated by a Z boson. FCNCs are processes in which the initial and final states have the same electric charge but a different flavor configuration. In the SM, FCNCs appear only at the loop level, and their rates are reduced due to the Glashow-Iliopoulos-Majani (GIM) mechanism. New physics models can be probed up to very high energy scales, often beyond the reach of past and current high-energy colliders. The authors focus on FCNCs that contribute to meson mixings arising from a Z boson. Mesons are made up of one quark and one anti-quark, and flavor-changing interactions are present at the one-loop level. The mass differences between mesons have been measured with great accuracy, and any new physics effect that could contribute to them is tightly constrained by data. The authors review FCNC in the SM, discussing how FCNCs emerge in the SM and why there is no FCNC at the tree level. They introduce the SM, showing why FCNC arises at the loop level, and discuss the key ingredients of FCNC, including the charged and neutral currents and the Yukawa-Lagrangian. The authors will demonstrate that one can choose the quark mixing matrices in such a way that FCNC bounds on the Z mass range between 0.13 TeV, rendering the LHC and HL-LHC much more promising probes for the Z bosons from 331 symmetry. The goal of their work is to show that the LHC and HL-LHC are capable of discovering Z bosons that mediate FCNC in agreement with FCNC bounds. The standard model, SM, of particle physics predicts the absence of flavor-changing neutral currents, FCNCs, at tree level. However, FCNCs can arise at one-loop level through diagrams involving the W boson. The Kabibo-Kobayashi-Maskawa (CKM) matrix plays a crucial role in FCNCs, governing the mixing of mesons such as B0, Bs, K0, and D0. The CKM matrix is parameterized as a 3x3 unitary matrix, with entries measured to be VCKM equals 0.97435 plus or minus 0.00016, 0.22500 plus or minus 0.00067, 0.00369 plus or minus 0.00011, 0.22486 plus or minus 0.00067, 0.97349 plus or minus 0.00016, 0.04182 plus 0.00085, 0.00074, 0.00857 plus 0.00020, 0.00018, 0.04110 plus 0.00083, 0.00072, 0.999118 plus 0.00031. The unitarity of the CKM matrix ensures the conservation of total probability for transitions between different quark flavors in weak interactions. The SM predicts the absence of FCNCs at tree level due to the unitarity of the flavor rotation matrix, VD_L. However, FCNCs can arise at one loop level through diagrams involving the W boson. The effective field theory approach to FCNCs involves interactions mediated by a Z boson, which distinguishes one fermion generation from the others. The mass difference of meson systems can be impacted by sizable flavor transitions caused by heavy gauge and Z boson. The effective Lagrangian for FCNCs can be written in terms of the coupling constants between the Z, boson and U-type and D-type quarks. After rotating to the mass eigenstate basis, FCNCs arise, and the effective Lagrangians for meson mixing can be derived. The mass differences of meson systems can be expressed in terms of the CKM matrix elements and other parameters such as the bag parameters, decay constants, and QCD corrections. The input parameters for the calculation of meson masses and mass differences are listed in Table I, including the experimental values for the mass differences of K, D, B_D, and B's mesons. The bag parameters and decay constants are also listed, which are used to calculate the mass differences. The QCD corrections, eta_K, eta_D, and eta_BQ, are also included in the calculation. Here is a combined summary of pages 5 and 6 of the research paper. The authors investigate flavor-changing neutral currents, FCNCs, in a simplified model and a concrete Z model, specifically the 331 model. They consider four meson systems, K0 K0, B0 decibels 0D, B0 SB0s, and D0 D0, and evaluate the lower bounds on the effective energy scale gamma and the mass of the Z field. In the simplified model, the authors use 5 different quark mixing matrices to derive lower bounds on gamma, which are summarized in Table 2. They find that the strongest constraint arises from the D0 D0 mixing for mixing 1, while the B0 SB0's transition leads to the strongest limit for mixing 4. The authors emphasize the importance of considering all 4 meson systems to obtain reliable results. In the Z model, the authors use the same 5 quark mixing matrices to derive lower bounds on the mass of the Z field, which are summarized in Table 3. They find that the lower mass bounds derived from FCNCs are subdominant compared to collider bounds for mixing 3, but for mixings 1, 2, 4, and 5, each meson system yields stringent bounds. The authors also provide Feynman diagrams illustrating the contribution of the Z-gauge boson in flavor-changing processes of the 4 meson systems. They plot the lower mass bounds in Figs. 4-7, overlaying collider bounds on the Z, derived from LHC data and projections for HL-LHC. In conclusion, the authors demonstrate the importance of considering all 4 meson systems to obtain reliable results and highlight the significance of FCNCs in probing energy scales beyond high-energy colliders. Here is a combined summary of pages 7 and 8 of the research paper. The authors investigate the influence of new physics processes on meson mixings, specifically focusing on the impact of different quark mixing matrices on the results. They utilize an effective operator approach and a Z model embedded in a SU, 3, C circled times SU, 2, L circled times U, 1, N gauge group. The study reveals that the meson mixings can significantly affect the size of the new physics contribution to meson mixing and the lower bounds on the new physics energy scale or the mass of the Z boson. The authors consider 5 different mixing scenarios, denoted as mixing 1 to mixing 5, which are defined by specific choices of the quark mixing matrices VDL and VUL. These mixings yield distinct contributions to the mass difference systems of various meson systems, including B0 decibels 0D, BSBs, K0 K0, and D0 D0. The results are presented in Figures 47, which display the Z contribution to the mass differences as a function of the Z mass for each of the 5 mixings. The figures also show the current and projected collider bounds, as well as the FCNC exclusion region. The study demonstrates that the lower bounds on the Z mass can be substantially weakened for certain mixings. In particular, the authors find that the lower bound on the Z mass can be as low as 3.0 TeV for mixing 3, which is much weaker than previously reported in the literature. This suggests that the LHC and HL-LHC can potentially probe Z masses larger than those excluded through FCNC studies, highlighting the importance of future colliders in constraining flavor-changing neutral processes. The authors conclude that the statement, FCNCs probe much higher energy scales than colliders unless a highly non-trivial flavor structure is present, needs to be revisited. They emphasize that FCNCs do not necessarily lead to constraints stronger than colliders and that future colliders, such as the HL-LHC, will play a crucial role in probing the Z, mass and flavor-changing neutral processes. Here is a combined summary of the 2 pages. The CKM matrix is not perfectly unitary based on experimental values, meaning that when one matrix is fixed to be unitary, the other does not turn out to be completely unitary. However, its characteristics remain similar to those of the CKM matrix. Using EQs 18 and 21, the findings are plotted in Figs 4-7. The references provided on page 9 cover a range of topics related to flavor-changing neutral currents, FCNCs, the Kabibo-Kobayashi-Maskawa CKM matrix, and the 331 model. These include papers on FCNCs in the 331 model, the CKM matrix, and quark masses and mixings. Some references also discuss the 331 RHN model and the flipped 331 model. On page 10, additional references are provided, covering topics such as lepton flavor violation, neutrino masses, and CP violation in the 331 model. Other references discuss the impact of FCNCs on particle decays, such as Villamizar decays, and the constraints on new physics effects in non-leptonic tree-level decays. The references also include a range of experimental results, such as measurements of the B0's oscillation frequency, and bounds on quark mixing, MZ, and Z-Z, mixing angle from FCNC processes in the 331 model. Additionally, some references discuss the importance of FCNCs in testing the standard model and its extensions. Furthermore, some references discuss the 331 model and its implications for particle decays and mixing, including a recent update on 331 model predictions for rare B and K decays. Others discuss the minimal flavored Z scenario and the impact of new physics on particle decays. The references provided demonstrate the breadth of research in this area, with a range of theoretical and experimental studies exploring the intricacies of flavor-changing neutral currents and the 331 model. This research paper presents a comprehensive review of the literature on D0 bar mixing, focusing on the experimental evidence and theoretical interpretations. The authors cite numerous studies from collaborations such as BABAR, CDF, and LHCb, which provide evidence for D0 bar oscillations. They also reference theoretical works on flavor-changing neutral currents, FCNCs, in the context of supersymmetry and new physics models. The authors highlight the significance of FCNCs in the B system, discussing their implications for CP asymmetries and rare decays. They cite studies on tree-level FCNCs, suppressed FCNCs in new physics models, and the role of lattice QCD in understanding neutral B-meson mixing. The review also covers the connection between FCNCs and other areas of physics, such as the CKM unitarity problem, WIMPs in 331 models, and dark matter searches at the LHC. The authors reference works on the connection between gamma rays, dark matter, and Higgs searches, as well as the constraints on the Z mass in 331 models using direct dark matter detection. Furthermore, the paper discusses the implications of new physics models for the muon anomalous magnetic moment and neutrino masses. The authors cite studies on the contributions of new physics to the muon G2, as well as the implications of 331 models for sub-V neutrinos. The review concludes by highlighting the importance of continued research in these areas, citing the need for further experimental and theoretical studies to constrain new physics models and understand the underlying mechanisms. The authors emphasize the potential for future hadron colliders to shed light on these open questions.